All right. Well, I hope that everybody's having a good day. We are going to go ahead and move on to our next lesson. We are finally done with the inverses of the trig functions. We talked about taking the reciprocal and special right triangles and all that good stuff. We're going to go ahead and start working on our big next unit, and it's over these identities right here. So using these identities, we're going to ultimately be able to solve equations, but first we want to get a little bit of practice with them. That means given expressions, we can rewrite those expressions using these identities. Okay, so we're just going to go ahead and go through one by one and see what you guys think. We'll do some examples and get some practice done. The only thing I need to mention next week, don't forget what is happening on Thursday the 24th. That's your test, okay, the first exam of the 6 weeks. So it will cover the inverses of the trig functions, which we've spent the past week looking over, and also it's going to cover this material here, okay, on all the identities. All right, so let's see what we got here. There's a lot of categories that we can break these identities into, but we're going to go ahead and start with what's called the reciprocal identities. Okay. Now, a lot of these you're going to be probably familiar with. Some of them not so much, but let's see what you guys think. What's the reciprocal of cosecant? Okay, it is sine. Now, one of the identities, the rules that we're going to be able to use is that cosecant, we can replace it with 1 over sine of theta. Or if I see 1 over sine of theta, I can replace it with cosecant. Think of this almost as a game. It's a puzzle that you're trying to figure out. These identities, these are the rules that we're allowed to use. Okay? So by the same token, sine, I could write it as 1 over cosecant of theta. Okay? Those are interchangeable. I can replace one with the other. Okay? Isn't that right, Genevieve? Right. So what's the reciprocal of secant? It was cosine, so I should be able to write that how? One over cosine of theta. That's absolutely right. Okay. So if I know that secant is the reciprocal of cosine, what's the reciprocal identity tell me? 1 over secant of theta. There you go. And what's the reciprocal of cotangent? Tangent. So I should be able to say that cotangent of theta is 1 over tangent of theta. And same token, tangent of theta is going to be 1 over cotangent of theta. Okay, all these rules are reversible and they work together. Okay, so these 6 are what we call the reciprocal identities. All right. Well, let's take a look at our quotient identities. Now, there's only 2 of those, tangent of theta and cotangent of theta. Now, we say quotient because you're going to create a fraction using 2 other trig functions. So tangent of theta can be sine of theta over cosine of theta. Okay. And this really starts to make sense when you think back to what we've done with the unit circle. What is tangent's ratio? It's always y over x, right? Okay. Always y divided by x. Well, remember, when we're looking at ordered pairs on the unit circle, sine always represents your y value. Cosine is always your x value. Okay? So any tangent, if I'm using the reciprocal identity, I can rewrite it as 1 over cotangent, or tangent can be simply sine over cosine. Okay? So cotangent, what do you think his ratio is? It would be x over y. So what trig function is x? Cosine over sine, yes. Cosine of theta over sine of theta. Okay. Those are what we call my quotient identities. All right. And here's the thing, you know, in my IS classes, I was definitely requiring the students to memorize those. They need to be very familiar with them. I don't know that that's so much necessary here because on your quizzes and tests, what can you do? Yeah, you can use your notes, so you'll always have those in front of you. So while you might not need to memorize them, you do want to be familiar with them, you know, how I can work with them. Okay, we're going to get to plenty of examples. Right now we're just listing all these identities. Now these are the biggest ones, the Pythagorean identities. Okay, more than anything else, these are going to show up a lot, and there's only 3 of them. Okay, so the first one, and probably the most common, is this one right here, sine squared of theta plus cosine squared of theta is equal to 1. Is that? Oh, turn it off. I'd heard something. I couldn't tell where it was coming from. I was like, what's there? Yeah. Okay. So sine squared of theta plus cosine squared of theta is equal to 1. All right. Okay. So I'm going to go back and kind of prove some of these to you in just a second, or how you can use this one to go ahead and get the other ones, but that'll be coming up in just a second. The other one is 1 plus tangent squared of theta is equal to secant squared of theta. This is a second Pythagorean identity. Okay. And the thing that can kind of get tricky about these identities is it's not just the direct identity you can always use, but you can use different versions of it. Like you can manipulate the equation that you're given here. Like for example, let's say I have sine squared of theta, okay, plus cosine squared of theta, and it equals 1. Okay. Let's say I want to go ahead and solve this for sine squared. All right, so I want to get rid of cosine squared. Well, just like any other equation, how would I do that? Yeah, just subtract it, okay, because it's positive here. So minus cosine squared of theta minus cosine squared of theta. Okay, now those are going to cancel because they're opposites. So I can see that sine squared of theta is equal to 1 minus cosine squared of theta. Okay. So this is also an identity, just manipulating the original one. Okay, so it's not just the identity as you see it. You can rearrange the terms and get different expressions. Okay, same thing for the 1 plus tangent squared is equal to secant squared. All right, and a lot of times when you're going through these, they may go ahead and use theta. They may use x or alpha or beta. The variable itself does not matter. Okay, that has no bearing on the identity. So let's say this last one here. It's going to be 1 plus cotangent squared of theta is equal to cosecant squared of theta. Probably the most useful identities you're going to have will be the Pythagorean identities. It's going to be these three guys right here. Okay. All right. So let me give you just a quick example before we go ahead and go on, like what the main purpose of the lesson's going to be. Let's say that I have this expression, okay, sine squared of x, okay, I'll keep theta, why not, of theta plus cosine squared of theta, and let's say I'm going to put that over, cosecant of theta. And let's say using the rules that I've seen so far, I want to simplify this into just a single trig function. Just one trig function. Okay. Well, is there anything that just stands out to you? Like what? Is there anything that's just really obvious? Like, do you notice any of those rules? Okay. What is sine squared of theta plus cosine squared of theta? According to this identity, it's just 1, right? So I'm going to replace that with 1 over cosecant of theta. Why does it equal sine of theta? That's exactly what the rule says. Yeah, what rule in fact? Okay. It's the reciprocal identity, right? 1 over cosecant is sine. So that whole expression just simplifies down to sine of theta. That's what you're doing. You want to be able to recognize the identities. What can I substitute? What can I use that can help me simplify these expressions? That's what this whole lesson is about. Marcus? Here is it. Okay. All right. Good, good, good. Okay. Now, let's go ahead and take a look at just some ways that we can prove those. The Pythagorean identities is what I'm going to go ahead and look at first. So if you know the basic identity, it's easy to derive the others. So we have sine squared of theta plus cosine squared of theta is equal to 1. Okay. Now, if I were to go ahead and say out of all these identities, if there was one you would absolutely want to know immediately, it's probably going to be this one right here, because this one can be used in order to get the other two identities that we were just looking at, the Pythagorean identities. Okay. So if we're looking at a circle, let's say a part of a circle in quadrant 1. So I have a terminal side that connects to this guy right here. Remember, we always connect it down to the x-axis. Okay, you know, we've got some kind of angle theta. Well, what trig function represents the x value? Remember, that's cosine. So this length right here would be cosine of theta. What trig function represents the y value? Sine of theta. Okay, and then remember the hypotenuse on the unit circle, the radius is always 1, right? Remember, that's why we call it the unit circle, because unit is just one length of measurement. Okay, so that this ordered pair right here on the circle, if I were going to go from the origin, okay, I'd have to go right cosine theta and then up sine theta. So that's nothing new. Remember, we're accustomed to seeing the ordered pairs on the unit circle in terms of cosine and sine, right? Cosine is the x value, sine is the y value, but what famous theorem always works with a right triangle? It starts with a P, the Pythagorean theorem. So if we say that cosine is your x value, sine is your y value, and the radius is 1 on the unit circle, well then a squared plus b squared should equal c squared. Okay, but here's the thing, whenever you square a trig function, you square the trig function itself. You don't square the variable, okay, in this case theta. So if I were to say cosine of theta squared plus sine of theta squared is equal to 1 squared. I just applied the Pythagorean theorem to the three sides, right? Okay. Well, when I square a trig function, I'm going to say cosine squared of theta. I'm not going to say cosine of theta squared. That's not correct. You're not squaring the variable, you're squaring the trig function, or whatever it is you're doing to it. So this one right here would be sine squared of theta, and of course it equals 1. Okay, and that's exactly the identity that we were talking about. Okay. Now, if anybody wants me to go a little deeper, I can use the ratios to go ahead and show you that, but I don't think it's necessary. Now, how can this Pythagorean identity, sine squared of theta plus cosine squared of theta equals 1, how can it give me the other two that we were just looking at? Okay. Well, I'm glad you asked. Okay. So here's what we're going to do. Let's go ahead and get one of the other ones. I'm going to take sine squared of theta plus cosine squared of theta is equal to 1. Okay. Well, I'm going to go ahead and divide all the terms by just the same value. So let's say I want to go ahead and divide through by sine squared. So I'm going to divide everything through by sine squared. Okay. Well, here's where some of the other rules are going to come in very useful to us. What is sine squared divided by sine squared? Yeah, it's just 1. Anything divided by itself is 1, right? Plus, now let's think about this. I've got cosine squared over sine squared. Does that look familiar? Does that look like one of my rules? Okay, there we go. If you go back up here, that is one of my quotient identities. Now, it says that, oh, look at it this one. Cosine divided by sine is cotangent, right? The only difference here is that it's cosine squared over sine squared. So if cosine divided by sine is cotangent, what's cosine squared divided by sine squared? It would be cotangent squared. Because cosine over sine is cotangent. But see, you keep the operation. Okay. Now, we also know from one of my previous rules, we know that 1 over sine of theta is equal to cosecant of theta, right? That's what we call a reciprocal identity. So if that's true, then what is 1 over sine squared? That would be cosecant squared. And doesn't that look familiar? Isn't that one of those other Pythagorean identities that we were just looking at? Okay. All right. Now, we're going to go ahead and do something real similar. Okay, I'm going to once again take that main Pythagorean identity, the sine squared plus cosine squared, is equal to 1. Now here I divided through by sine squared. What do you think I'm going to divide by in order to get the other one? Cosine squared. I'm going to divide each of these by cosine squared. Okay. Well, let's see. Cosine squared divided by cosine squared. What is that? That's 1. Okay. Now, we have an identity that says tangent is equal to sine divided by cosine, right? So what is sine squared divided by cosine squared? That would be tangent squared. See, it's the same rule. I'm just applying the squared to it. Tangent squared of theta. Now, we also have another rule. It's a reciprocal, one of the first ones we looked at. It says 1 over cosine of theta equals secant of theta. So what's 1 over cosine squared? Okay. And there's your third identity. Okay. So really, if you know this guy right here, if you know the sine squared plus cosine squared equals 1, you can actually use it to get the other two really easily. Just divide by sine squared or divide by cosine squared. Okay. Well, let's go ahead and look at just some simple examples. Okay. Let's look at some simple examples. We haven't gotten to all the identities yet, and that's okay. Let's look at this one. Example 2. Use a quotient identity to simplify and rewrite. Now, one of the number one rules, there's a ton of different strategies for simplifying this, but probably the best way to start is to always rewrite everything in terms of sine or cosine. Okay. If you write everything in terms of sine and cosine, a lot of times that helps you identify what it is you're looking at. So let's see. Cosine of beta times tangent of beta. Again, the variable doesn't matter. You'll notice this one's using beta. Okay. This one's using x. This one's using theta. Changes nothing. Okay. Does not change a thing. All right. Well, let's see. The cosine, I'm going to leave that as is. Cosine of beta times. Now, it says use the quotient identity. What was the quotient identity? What's it talking about? Let's see. If I come back over here, the quotient identity, okay. So what should tangent of beta equal? Okay. Now, with what variable? Beta. See, that stays the same. So it should be, according to that rule, sine of beta over cosine of beta. Okay. Now, do you notice anything that can happen? Yeah, the cosines are going to cancel out. That's exactly right. Because if it helps, put this guy over 1, because now you're multiplying two fractions. If the cosines cancel, well, then this is equivalent to sine of beta. That's all we're doing. We just want to take these expressions and use those rules to simplify them as much as we can. Okay. How are we doing? Doing good? Okay. All right. Now let's try the next one. Okay. Now this won't always be done, but I would say probably 95% of the time, the best way to simplify these is to rewrite everything in terms of sine and cosine. Okay. So let's break this up. I've got secant times cotangent times sine. Okay. Well, how am I going to write secant as sine or cosine? What rule will I use? Okay, so secant is the same as what? So 1 over cosine of x. And see, even though we have the variable x, the rule still applies. Okay, times. Okay, cotangent. So is that sine over cosine or cosine over sine? Okay, cotangent is always cosine over sine times. And then sine, we're trying to rewrite everything in terms of sine and cosine, so it's going to stay the same. Yeah, I'll just even go ahead and put it over 1. Okay. And do you notice anything? Yeah, the cosines cancel, the sines cancel. So this expression actually has what value? 1. It's just like if you were going to play any kind of game, in order to play the game, you have to know the rules. Those identities are our rules. Okay? That's all we want to do. What do you notice that we could use to help us out? Okay. Let's try number 3. It says use the idea of decomposing fractions to simplify and rewrite. Okay. So I want to rewrite this in terms of one trig function. One trig function with no fraction. Okay. Now, here's the thing. There are rules, when we're talking about fractions. If you were to have a fraction, like let's say a divided by b, okay, you can separate the numerator from the fraction, but still have it connected by multiplication. Okay. Does anybody want me to give you an actual example just to kind of show you that? Okay. Let's say we have the fraction, I don't know, 2/5. Okay. So 2/5, well, that would be equivalent to saying 2 times 1/5. Okay. As long as you're multiplying, you can just pull that right out in front. Okay, well, why is that useful here? Well, let's see. I can do the same thing. Doesn't matter that it's a trig function. So I can take cosecant of theta, and that'll be times 1 over sine of theta. Okay. So maybe if you go ahead and separate the fraction like that, do you notice an identity now? What is 1 over sine theta? That's cosecant. So cosecant of theta times, okay, cosecant of theta. So what do you think cosecant times cosecant would give me? There you go. Think about the trig function as just a variable. X times x would give you x squared. So this guy right here would give you cosecant squared. Okay. And that's what's going to happen a lot of times for us in the beginning. We're just going to rewrite it as a single trig value. But not all expressions are just going to become a single trig value. Could be a binomial. It could even still be a fraction potentially. Okay. All right. And the one thing I want to go ahead and point out to you, and this is what can confuse folks, is there only one way to work the problem? No, there's going to be a lot of different ways to get the same answer. It really depends on what identity you see and you want to use. Okay, like on this one here, let's revisit it for a second. If you stick with the idea that you always want to change every trig function to sine and or cosine, okay, well then cosecant, okay, wouldn't that be 1 over sine? That's 1 over sine of theta. And see, we're still divided by the sine of theta. Well, why don't we still go ahead and just apply that rule? I can pull this numerator out in front. So this would be 1 over sine of theta times 1 over sine of theta. Is everybody okay with how I got that? Okay. All I did, cosecant became 1 over sine, and I just pulled that out to the front. So that's that 1 over sine times the 1 over sine. Now just multiply straight across. What's 1 times 1? 1. What do you think sine times sine is? Sine squared. Okay. Now we know that 1 over sine is cosecant. So what's 1 over sine squared? Cosecant squared. Okay. And that's the trick. Okay. There's no really a right or wrong way to do these as long as you're following those rules. Okay. As long as you're following those identities, there can be a ton of different methods to get to what you're trying to get the answer. How we doing? Okay. All right. Let's try the next one. Okay. Now, I'll go ahead and tell you that this one will simplify down to a single trig function. Okay. Now, even though it's a single trig function, it can still have an operation. I mean, it can still be multiplied by a number. It can still be squared, cubed, whatever. But they'll just be the one trig function. Okay. Do you guys want to try one on your own? Okay. Now, here's what I would do. I'll go ahead and give you a hint. If you're going to add or subtract fractions, Like if I had x over z and I wanted to add that to y over z, okay, you have to have a common denominator, right? So what would that be if I simplified it? It would be x plus y over the single z, right? Well, the nice thing about mathematics, okay, a lot of these rules that we work with, they're all reversible, okay? So I can actually go from one to the other. And that's probably what I would recommend you do here, okay? Instead of changing everything, to sine and cosine, you could absolutely do that, but see, then you're going to have a fraction over a fraction, and it might get a little complicated, okay? I would go ahead and say break these two numerators up over the common denominator. So I would say sine of x over cosecant of x minus, because that's the symbol I have, and then cosecant of x over cosecant of x. I might approach it that way. You see how it's a lot easier now than a big fraction with littler fractions? Okay. So let me give you a little bit of time to take a look at that and see what you think. Okay. Now, I will tell you that you are going to be using one of the Pythagorean identities as well. If you simplify this correctly, you should see a version of one of them, one of those three. And perfect opportunity if you want to go ahead and visit with your villain buddy, those around you, see if they're doing the same thing. What rule are they using? This one will become a single trig function now. Sorry, I'm eating ice while I said that. Okay, now does anybody think they know what that final answer should be? What's the single trig function this should simplify to? Sure, what do you think it is? Yes. Now, use the Pythagorean identity to finish it up. Okay, so let me catch up with Brandon. Okay, let's go ahead and run through this. Now, everybody's okay with how I broke it apart into the two fractions? Okay, well, what's cosecant over cosecant? That's 1. So we definitely have that minus 1. Okay, but walk me through, how am I going to simplify sine over cosecant? Okay, so I can pull the sine x out over. Okay, so I just separated it. And what is 1 over cosecant? Okay, so Brandon says use the reciprocal identity. So 1 over cosecant is sine of x, right? And sine times sine That's going to give me sine squared, right? Okay, now he is absolutely right. But here's the thing. Remember, I said there was going to be a Pythagorean identity to help you here, because we were going to simplify this to just one trig expression. So what Pythagorean identity do you think we're using? It is sine squared plus what? Cosine squared is equal to 1. And again, we have them on the other page as theta, but remember the x's change nothing, right? So here's the thing. I want to rewrite this equation so that I have sine squared of x minus 1 on one side. Okay. So the first thing I need to do, let's go ahead and subtract the 1 over, right? So this would be sine squared of x plus cosine squared of x minus 1 is equal to 0. There you go. See, I've got the sine squared of x minus 1, but I want that by itself. I want to see exactly what I do here. So I'm going to subtract the one term I don't need. Minus cosine squared of x minus cosine squared of x. Those are going to cancel. So sine squared of x minus 1 equals, what would that be? What's 0 minus cosine squared? Negative cosine squared of x. And remember, this is what I was saying just a little while ago. It won't always be the direct identity. It may be some modified version of it. Because isn't this statement here, sine squared minus 1 equals negative cosine squared? That is equivalent to the original identity. Okay. So now I'm just going to use substitution. Sine squared of x minus 1 is negative cosine squared of x. Okay. How we doing? Now, this is just the first day. It's going to take a little bit of practice, but I think you're going to be okay. We're going to spend time on this. This is nothing that we're going to rush through. Okay. Let's see what that next section says. Factor completely. Okay. Now, we reviewed factoring way back in the first semester. If we want to factor expressions that have trig functions, it's actually a lot easier than you think. All we need to do is just go ahead and replace the trig function with some kind of variable. Okay. Like, let's say, for example, sine of x, give me a letter. Out of all the, okay, so L. All right, so we're going to say sine of x is equal to L, right? Okay. So I'm just going to replace this. So that would be 2L squared, because L is sine, right? And then minus 3L plus 1. Okay. Doesn't that look a lot nicer and more inviting than the one with the trig expression? Okay. Now, does anybody remember how we factor a trinomial? What was that method that I liked? What's my dad drive? He does not drive a Range Rover. There you go. My father drives a red Mercedes convertible. Do you guys remember that? Let me go ahead and walk you through the process. Okay. No, he does not. My father drives a red Mercedes convertible. Okay. Actually, my dad drives a maroon Chevy, but that's something different. Okay. Okay. So the first letter in every word was a step in the process. Like when you hear PEMDAS, please excuse my dear Aunt Sally. Parentheses, exponents. Okay, you know the words that goes along with them, right? Okay. Well, the first M stands for multiply. So I want to multiply the first coefficient by the last. So what's 2 times 1? 2. Okay. Now, the F stands for factor. Okay. Well, this is pretty nice for the first example. What are the only factors of 2? Okay, now it's 1 and 2, but here's the catch. We need 2 numbers that'll multiply to give me that positive 2, but they have to add to give me negative 3. So in this case, they both have to be negative. If you can find the 2 numbers that satisfy those conditions, guaranteed you're going to get it factored correctly. That is the most important step in the process. Okay. Now, does anybody remember what the D stands for? Divide. We divide. In fact, what am I going to divide by here? We always divide by the leading coefficient. So I'm going to divide by 2. I'm going to divide by 2. What's the R stand for? Reduce. That's exactly right. There you go. It's coming back to you guys. So if it's a fraction that can simplify, we go ahead and do so. So negative 1/2 won't reduce. But negative 2 divided by 2, we know that's what? We know that's negative 1. The only trick here is that when you reduce, you always want to leave it as a fraction. So I'm just going to say negative 1 over 1, because that is negative 1, right? Okay. What does the other M in Mercedes stand for? Not manipulate. I guess you could look at it as manipulate. But we say move. I like to move it, move it. Okay. Surely that's from your childhood, right? You know. Okay, all right, make sure. Okay, so you say Home Alone. Different movie. All right. So here we go. Now remember, we're using L to do this. All I want to do is move these numbers to the groups, and I have my factored answer. Now, would that be negative L plus 2 or 2L minus 1? 2L minus 1. Remember, we always start from the bottom and work our way up. The denominator is the coefficient. So what would negative 1 over 1 be? 1L minus 1. Okay. So we went ahead and factored this. We've got 2L minus 1 times L minus 1, right? Okay. Well, now we'll just go back in and go ahead and plug in our trig function. We said that L was sine of x. So the factored version should just be 2 sine of x minus 1 times sine of x minus 1. Remember, this method only works for a trinomial if it has how many terms? If it has 3. So see, you don't even have to deal with that trig function until the very last step. It's just like you're factoring a normal polynomial. Okay. How we doing? Good? This making sense? Cool, cool, cool. All right, well, I'll tell you what, we'll go ahead and stop there.